Today I want to take a look at the halogens, also known as group 17 in the periodic table. Being nonmetals, they're poor conductors of both heat and electricity. They show a gradual change in their property or state. And we start off with fluorine and chlorine existing as gases, bromine as a liquid, and iodine as a solid. That happens because as we move down the periodic table, there's a gentle increase in the melting point of the substance. Chemically speaking, this is a particularly reactive nonmetal family. That reactivity increases as we move up the table. If we take a look at why that happens, all members of this family have an effective nuclear charge of 7+. But what happens is the distance of the nucleus to the outer level electrons is increasing, as you can see here from the electron configuration of both fluorine and chlorine. That increased distance results in a decrease of attraction for electrons. All halogens want to gain electrons. As a result, they tend to form ionic compounds with metals and covalent compounds when they bond with nonmetals. Here again we'll use table salt as our example. It tends to gain a single p electron to have a configuration of a noble gas. Hence they tend to form X1, X-1 ions. Here's an example of hydrogen sharing an electron with chlorine, two nonmetals, and this results in a covalent compound. In unit number 4 we'll take a little bit more closer look at electron dot diagrams and the difference between ionic and covalent compounds. Let's take a look at the reaction specifically with metals and nonmetals. I'll use table salt again as my standard example. Sodium, the metal, reacting with the halogen, in this case chlorine. What will happen in this case is the metal will lose that 3s electron, donating it to complete the octet of the chlorine ions, so it can then have a stable configuration resembling argon. That then results in the formation of each of these species developing a charge. The metal becomes positive through the loss of the electron, and the halogen becomes negative through the gaining of an electron. These opposite charges attract, and as a result, we tend to have an ionic compound. The balanced chemical equation for this is shown here, first of all, not balanced, and now in its balanced form. Let's look a little bit more closely at the reactivity within the family itself, but I want to introduce a few terms. First of all, the halogen. We recognize that because it represents the atoms without a charge. Most of these substances form diatomic species, meaning H things like Cl2, F2, Br2. In this state, the atoms don't possess a charge because they're sharing electrons with each other. However, when it bonds with a metal, it tends to gain an electron and forms what we call a halide. It's no longer a halogen, and we call this the halide ion. I want to look at reactions between halogens and halides. Also, let's quickly review the reactivity again, fluorine being the most reactive member of the family and iodine the least reactive. So if we were to bubble chlorine gas through a solution containing sodium bromide, would this following reaction happen? In order to understand it a little bit more closely, I'm going to express the reaction as a net or an ionic equation. You might recall that in ionic equations, species that are aqueous break apart into ions. So here, both the sodium bromide that is aqueous and the sodium chloride, which are aqueous, would break apart into their corresponding ions. So down below, we have the ionic equation. Chlorine, being higher up in the periodic table than bromine, is more reactive. If I take a look carefully at the ionic equation, I can recognize here that bromine possesses that extra electron. Chlorine has no charge. Since chlorine wants the electrons more, the reaction will proceed as shown in the equation. If I reverse the two species involved, so I now have bromine liquid mixing with a sodium chloride solution, and again I express it as an ionic equation, here I can see chlorine has the electron. Chlorine wants the electron more than bromine, and since it already has it, there's no need for these species to react. So this combination would not react. Finally, there's a quick test that we should be familiar with to recognize the presence of halides in water. When we add silver ions to these solutions, they'll produce slightly different colored precipitates or solids that cause the solution to go cloudy. So for instance, the addition of silver ions to a solution that contains chloride ions will cause the formation of that white precipitate or white solid. If it contains bromide ions, the addition of silver ions will form silver bromide. That's slightly off-white colored precipitate in this case. And finally, the yellowish precipitate is produced when silver ions mix with iodide ions. So that covers a quick look at group 17, or the halogens in the periodic table. In our next program, we'll take a look at the oxides of period 3 as we move from left to right from sodium across the periodic table. Thanks for watching, and don't hesitate to post any questions.